Most people look out an airplane window, see the wing bouncing in turbulence, and assume that's the last place you would ever want thousands of liters of fuel, because inside that moving wing is exactly where airlines store most of it, not in the cabin, not in giant tanks under the floor, but inside the wings themselves. At first, that sounds backwards. Wings bend, twist, and carry huge loads. Why put flammable fuel in the most stressed part of the airplane? Why not store it in the fuselage, where everything feels solid and protected? The answer is that putting fuel in the wings doesn't create one advantage. It solves several major problems at the same time. And once you understand them, the design starts to look less risky and more ingenious. The first reason is space. The fuselage is the most valuable area on a commercial aircraft. That tube-shaped cabin is where passengers sit, cargo is loaded, and equipment is installed. Every meter of that interior can earn money. Seats generate ticket sales. Cargo space generates freight revenue. If airlines had to dedicate a large section of the fuselage to fuel tanks, they would lose seats, lose cargo volume, or both. That can make routes less profitable immediately. But wings are different. Nobody sits inside them. No luggage goes there. Their internal volume already exists because the wing needs structure to support flight loads. Using that empty internal space for fuel means the airplane gains storage capacity without sacrificing cabin revenue. So the wings offer something rare in aviation: useful volume that costs almost nothing commercially. The second reason is balance. Aircrafts are carefully designed around the center of gravity. That is the point where the airplane's weight is considered balanced. If it shifts too far forward or backward, handling becomes less efficient and, in extreme cases, unsafe. Now think about a long flight. A large airliner can burn tens of thousands of kilograms of fuel during a journey. If all that fuel were stored mainly in the fuselage, then as it disappeared, the aircraft's balance point could move significantly. Pilots and systems would constantly need to compensate. That usually means more trim adjustments, more drag, and higher fuel consumption. But wings sit close to the aircraft's center of lift and near the ideal balance zone. If fuel is burned evenly from left and right wing tanks, the center of gravity changes far less during the flight, so the aircraft stays more stable from takeoff to landing, with fewer penalties in efficiency. Then there's the third reason, and this is the one many people never hear about. Fuel in the wings actually helps reduce structural stress. When an airplane is flying, lift pushes the wings upward. At the same time, the weight of the fuselage, passengers, and cargo pulls downward through the middle of the aircraft. That creates enormous bending forces where the wing joins the body. Engineers call this area the wing root, and it is one of the most heavily loaded parts of the airplane. Now, add fuel inside the wings. Fuel has weight, so it pulls downward along the span of the wing. That downward force partly counters the upward lift trying to bend the wing upward. In simple terms, the fuel acts like a built-in counterweight. This reduces stress at the wing root, allowing engineers to design a lighter wing than would otherwise be required, and lighter aircraft burn less fuel over their lifetime. This is one reason fuel loading order matters. Aircraft are typically designed so wing tanks are filled first and used strategically, especially when the aircraft is heavy. At takeoff, total weight is highest, so wing loads are high too. Having fuel in the wings provides the greatest structural benefit right when it's most useful. As the flight continues, the aircraft becomes lighter, so the need for that extra relief decreases naturally. That is elegant engineering. The benefit fades at almost the same rate the need fades. The fourth reason is efficiency of design itself. Inside a wing are spars, ribs, and sealed compartments that already exist as part of the wing's skeleton. Engineers realized they could seal these cavities and use the wing structure itself as the tank. That means no need for large separate containers with extra walls, mounts, and hardware. Instead of adding another heavy system inside the airplane, the existing structure performs two jobs at once. First, it supports the airplane, and second, it stores fuel. One challenge is maintenance. The inside of a fuel tank must remain sealed despite years of vibration, wing flexing, temperature changes, and fuel exposure. Over time, sealants can degrade and leaks may develop. Repairing those leaks can be difficult. Technicians may need to inspect and work inside confined spaces within the wing, which is time-consuming and can take an aircraft out of service. Modern materials and improved sealants have made this better, and newer aircraft continue refining the concept, but it remains one of the trade-offs of the design. Some specialized aircraft use additional tanks elsewhere. Long-range jets may carry center tanks. Certain military aircraft use external tanks or self-sealing systems for survivability. Supersonic aircraft like Concorde even moved fuel between tanks in flight to control balance at different speeds. But for most airliners, the wings remain the smartest primary location because with one decision, engineers solve 4 major problems. They preserve cabin space, they maintain balance, they reduce structural loads, and they avoid adding unnecessary weight. So the next time you watch an airplane wing flex in turbulence, remember this: that movement is not a sign of weakness. Wings are designed to flex, and inside them is fuel doing more than waiting to be burned. It is helping the aircraft carry passengers, stay balanced, reduce stress, and fly efficiently, all at the same time. The part that looks most vulnerable is actually one of the smartest parts of the entire machine.